Welcome back to another video in our high school chemistry series. I'd like you to tell me what this is. So go ahead and take a moment and see if you can figure out what it is. So this is the first periodic table. So Dmitry Mendeleev is the person we credit with the creation of the first periodic table. It's not the first to put the elements in a list or their masses in a list, but he is the first to actually show the periodicity and the repeatability. He included some question marks, which I think is one of the most brilliant things about this, is that he was able to predict new elements and elements we hadn't discovered yet. So this is another periodic table, a much more modern periodic table with just tons of information. It has some charge information. In the periodic table, the columns are called the groups or families, and the rows are called the periods. So groups or families tend to have similar behaviors because of similar electronic structures. Periods change as they go across, and we'll talk about periodic trends a little later. So this is a really common one. This is what you'll see in AP chemistry. You'll notice there's no names. It's just the element symbols, the atomic number, and the average atomic masses. We're going to talk today about the periodic table and how it relates to electron structure. So we talked about the s orbitals, the p orbitals, different energy levels, and things like that. Well, the periodic table is actually arranged so the first row has your first energy level, your second energy level, your third. Gets a little bit dicier once you get down here, but the S and the P are still 4, 5, 6, 7. The D block, actually it's 3D instead of 4D. It has to do with stability and energy levels and things like that. On your own periodic table, you should label this as the S block, this as the P block, this as the D block, and this as the F block. What that tells you is that the electron configuration, which we're going to be learning about just a couple of minutes, is going to end typically with, if it's in this row, it's going to end in 4D. If it's in this row, it's going to end in 4F, and so on. Now, the electron configurations are the elements of the lithium three series. So hydrogen is 1s1, helium 1s2, lithium 2s2 is how it ends, lithium is 1s1, it's how it ends, beryllium 2s2, boron 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. This is how the electron configuration ends, not necessarily how it starts. But what you assume is that everything oxygen has 1s2, 2s2, 2p4. I'm going to show you how to do that and how to develop that series. So one of the things to remember when we're talking about this is that electron spin describes the behavior direction of spin, just to review, and that the possibilities are +1/2 and -1/2, and that because of this, Wolfgang Pauli said that two electrons occupying the same orbital must have opposite spins. Well, here are electron configurations showing spin notation or orbital notation. You'll notice that here with lithium we have a 1s orbital, we have one 2s orbital, and we have 3 2p orbitals. As you'll recall, that's how many there are, and you should be able to remember those shapes. So the orbital notation of lithium has 2 electrons in the 1s orbital and 1 electron in the 2s orbital. Beryllium, it's 1 upspin, 1 downspin, 1 upspin, 1 downspin, so it's 1s2, 2s2. Boron, carbon, nitrogen. You'll notice that we actually put 1 in each of the 2p orbitals before we start doubling up. We don't double up until we get to oxygen because they want to be half filled before they're completely filled. So fluorine gives us a similar idea, and neon fills all of those. This shows you a lot of information, a lot of your notation, a lot of your electron configurations, but it doesn't tell you how to do it. So this is the off-bow chart. You really should put this in your notes. The reason for that is because this is how you're going to build up your electron configurations from the ground up. Aufbau is actually a German word meaning to build up. So, first, let's look at hydrogen. So the questions you want to ask yourself when you do this, the first question is how many electrons does it have? Hydrogen has 1 electron. So how many electrons does it have? It has 1. And we start at the top with 1s, and we say 1s with a superscript 1. So we follow and fill in order as it follows here. The things to remember are that in all of the s orbitals in a given level, we can only have 2 electrons. In all of the p orbitals in a given level, we can have 6 electrons. In all of the d orbitals in a given level, we can have 10 electrons. In all the f orbitals in a given level, we can have 14 electrons. So let's look at another one. Hydrogen, again, 1s1. Helium has how many electrons? 2 electrons. So helium with its 2 electrons, we go 1s, because 1s is the level, and then how many electrons? 1s2 is how many electrons. So that 1s orbital is actually filled once you get to helium. So our next one is nitrogen. How many electrons does nitrogen have? And what is the electron configuration? It has 7 electrons, and we go 1s2, follow the chart, 2s, we can only have up to 2 in each set of s, and then from there we go to 2p, we have 7 minus 4 gives us 3 left, so 2p3. Next comes carbon. How many electrons, and what is its electron configuration? Carbon has 6 electrons. Carbon's electron configuration is 1s2, 2s, 2 electrons in that, and then go to 2p. It can hold up to 6 electrons, but we're only going to need to put 2 in there for carbon. Our next is silicon. How many electrons does silicon have, and what is its electron configuration? Silicon has 14 electrons, and just to remind you, you figure that out by looking at the top number on the periodic table. The atomic number is how many electrons it has. So the silicon, we go 1s2, 2s2, 2p6, because we need all 6 in there, 3s2, and 3p2. You'll notice that it ends in P2 and carbon ends in P2. You'll notice that they're right on top of one another on the periodic table, and they're both in the second column of the P block. Titanium. Titanium has 22 electrons, and so we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and notice we don't go from 4s to 4p, but we follow the curve and we get to 3d2 to finish up our electrons. Now, you'll see in a lot of electron configurations, you'll see 3d2 before 4s2 because they put them in the order of energy level, not necessarily in the Aufbau order. The Aufbau order is good for being able to create those electron configurations, but the standard is actually to write them a little bit differently. So in questions, you'll see them differently. But you'll notice that all of these, the 1s2, 2s2, 4s2, 3d2, they'll all be present, but maybe slightly out of order. Chlorine. Chlorine. It has 17 electrons. So we follow 1s2, 2s2, 2p6, 3s2, 3p. It should actually be 3p5, not 3p6. So you'll notice that this is wrong because it should be 3p5. Iodine. Iodine has 53 electrons. So 1s2, 2s2, 2p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. You'll notice it and chlorine are in the same column, so they should both end in p5. What about uranium? It's way down there, has a huge number of electrons. What about plutonium? There's got to be an easier way to do this. And there is. So there's something called the noble gas configuration. And what you do is you take the element that you have and you look at the noble gas before it. So if we look at something like calcium, calcium has 20 electrons, but the noble gas before it, and the noble gases are the gases in this column. The very last column on the periodic table is called the noble gases. So right before that is argon. You would put argon in brackets, and basically that says, I have all of the electrons that are in argon. And then what you do is you count 1, 2, 3, 4. So on the fourth row is where calcium is. That's where we're starting. So we would start at 4s because we're on the fourth row. We would take the number of electrons calcium has, which is 20, subtract the number that argon has, which is 18. We're left with 2, and we start filling at 4s. And so calcium would be argon in brackets with 4s2. So let's actually do those ones that we just did, but do them with the noble gas configuration. So what's the noble gas before hydrogen? There is none. It's the first element, so its electron configuration doesn't change, 1s1. What about helium? Helium is the first noble gas, and so its electron configuration does not change, but everything after helium would. So, nitrogen. What is the noble gas before nitrogen, and what's its noble gas configuration? The noble gas before nitrogen is helium, and its noble gas configuration, we would take the electrons that helium has, which is just 2, and we'd be left with the remaining electrons. Nitrogen is in the second row, and so we'd start at 2s2, 2p3. You'll notice the ending is the same as it was when we did it the other way. If it doesn't come out the same, something has gone wrong. Carbon. The noble gas before carbon is helium, and it's 2s2, 2p2. Silicon. Again, silicon has 14 electrons, but we say that neon is the noble gas before it, and it's on the third row, so we start at 3s2, 3p2. Titanium. Argon is the noble gas before it. We start at 4s, so 4s2, 3d2. You'll notice that I did that reverse that you'll sometimes see here. Chlorine. Chlorine, the noble gas before it is neon. It's on the third row, so 3s2, 3p5. Iodine. Krypton is the noble gas before it, so 5s2, 4d10, 5p5. I'd take either order of those. Uranium, so now we can actually start dealing with uranium. Radon is the noble gas before it. It's on the seventh row, and so we start at 7s2, and then go up here to 5f4. Plutonium, radon again on the seventh row, radon 7s2, 5f6. One last thing. What about if you have a charge? So chlorine with a -1 charge means it has one more electron, which means to the electron configuration we add one more electron. So neon in brackets for the noble gas configuration, 3s2, 3p6. Magnesium with a 2+ charge means it actually has 2 less electrons. So helium, 2s2, 2p6.